Today, we will mainly talk about the how to cut thick metal with 30 kilowatt fiber laser, and we will start with the machine operation and then move into the parameter optimization to make the scope clear from the start. Today's cutting range includes two main areas. First, 20 to 6 millimeter carbon steel, and second, 20 to 40 millimeter stainless steel. So this is not a general talk about sheet metal cutting. Today, we are focusing on thick metal. And as always, I'm joined by Frank Vitali, our guest.
Hello everyone. Hello Dennis.
Hello Frank. So before we get started, we will have a quick note. This month, we will also run a separate promotion live stream. If you'd like to join and unlock the webinar exclusive benefits, email the code GLOBALUM1 to info@bodor.com. You will have the chance to unlock the limited time purchase bonus, including up to 5,000 worth of accessories, and also including a chance to get the laser head, a free laser head, and also to even the chance to receive a handheld laser welding machine for free. And today we will go through the practical side of thick metal cutting with 30 kilowatts. We will look at how the machine is used and how the gas selection affects the process, how parameters are adjusted, and how these choices appear in real cutting results. So, we also touch on the speed difference kilowatts, the difference between plasma and laser cutting. And we also have a showcase of our real customer case in Germany. So Frank, let's have a look at the cutting results of 30 kilowatts to cut the ultra thick carbon steel. What do you think people who watching the footage will focus on to watch first, Frank?
We can talk about first some introduction about process, about how to start from start to machine to take off the machine, to power off the machine. And also I will start with the one basic question, not only whether the machine cuts through the plate, but also what kind of part comes out after the cut. So in other words, people should look at the age, the consistency of the profile, and the section quality, the holes, the corners, and more generally, all complete and how clean the final result really is. And because once you move into thick metal cutting, the real question is no longer only penetration. The real question is whether the part comes out in a condition that makes sense for your production.
So this first section is really about defining the target results, right?
Yeah, yes, exactly. And that becomes even more important once you get into 20 to 60 millimeter carbon steel and 20 to 40 millimeter stainless steel. And because at those thicknesses, the difference between it cuts and it cuts well becomes much more obvious.
Yeah, right. Yeah. So from the beginning, the point is not just the high power by itself.
Yeah.
The point is using 30 kilowatts to cut thicker material, more cleanly, more reliable, and in a way that gives you a better part in the end. And once the visual goal is clear, the next question is simple. How do you get there in a stable and repeatable way? And that brings you directly into the first block of today's webinar, how to actually operate a 30 kilowatts machine.
Let's start from the very beginning. Powering on the machine.
Okay.
Yeah.
It may sound more very simple, but actually the order matters a lot, right?
Yeah, exactly, Dennis. if the sequence is wrong, it can affect it can affect safety and machine stability. So the correct process is first, obviously, turn on the main power.
Okay.
And second, the voltage stabilizer, if equipped. After that, the air compressor. Then we move to the electrical cabinet, followed by the cutting gas, and next, we can start the chiller. And the chiller, and then the laser source, and finally the control software that we use Bodor Thinker, but is for all the software.
Yeah, of course.
Yeah. And
so basically, we go from the supporting system and to the core system.
Yes, this is a good way to understand it. And before we start cutting, we need to go through the preparation process.
And Frank, I think this is one of the most important parts, right?
Yeah, absolutely. In the real production, many cutting problems actually come from poor preparation. Yeah, so if this step is done correctly, you can avoid most issues before they haven't happened.
Yes.
Yeah. So let's start with the first step, machine homing.
Machine homing.
Yeah. Homing.
Okay.
It sounds simple. Yeah, but there is actually more behind it. When we return the machine to homing origin, we are not just resetting position. We are making sure the entire coordinate system is correct.
Yeah.
And the machine follows a specific sequence. Yeah. First, the z-axis moves up. This is to avoid any collision with the material. And then the x and the y-axis return to their zero position. Yeah. After returning to the machine origin, they appear in front of the coordinators of each axis in the machine tool control bar. Yeah. So the machine knows exactly where it is in the space.
So even it looks like a simple step, it's actually the foundation of the entire process, right?
Yeah.
Okay. And now let's look at the nozzle. Frank, this is a very small part, but it's very important, right?
Yeah, nozzle. The nozzle directly affects gas flow and the cutting quality. So we always check it before cutting.
Okay. But how do we check?
Three things: appearance, installation, and the size. First, appearance. We check it. The nozzle is warm, damaged, or blocked. And we also make sure the outlet is still round. If the nozzle is not in good condition, the gas flow will not be stable. Yeah. Second, installation. We make sure the nozzle is tight and not shaking. Yeah. If this is loose, it will affect the beam and the gas flow. And third, the sides.
Okay.
Yeah, the sides. We choose the correct nozzle type and the diameter based on the cutting job. Different material and thicknesses need different nozzles.
Yes.
Yeah.
So three things.
Yeah.
Condition, installation, and size.
And size. Yeah.
Okay.
Yeah. And now we talk about the lens.
And Frank, how do we quickly tell if the lens is clean?
Yeah, we use the red light.
Red light. Okay.
Yeah,
okay.
we use the red light. Place a piece of paper about 200 millimeters below the nozzle. Then turn on the red light. If the light spot is clean and uniform, the lens is in good condition. If you see black spots, the black spot usually means the protective lens is dirty.
Okay.
Yeah.
Seems very just sample check, but very effective, right?
Yeah, exactly. Yeah.
And what if we see some black spots?
Then we need a deeper check using paper.
Paper.
Yeah.
Just the same with the paper you just mentioned, a simple paper.
Yeah, paper.
Okay.
Photo paper.
Okay.
Yeah. We set the machine parameters and define the laser onto the photo paper. If black spots appear on the paper, it means the optical path is contaminated. Yeah.
So this helps us confirm whether the problem is inside the optical system, right?
Yeah, yeah.
And how do we make sure the result is accurate?
We test multiple times. We apply the same laser spot in different focus positions. Yeah, if the black spots appear in the same position each time, then the lens is definitely contaminated, dirty. Okay. If the spots change, then it may be something else.
So we don't just rely on one test.
Yeah, exactly.
Okay.
We verify it. All right. Next, we talk about beam center. We set the focus first. We set the focus to 0. Then we go into the maintenance page and open focus control. After that, we set the burst parameters: power, frequency, and pulse. Then we use a small nozzle and place tape under it.
Okay.
Yeah.
And now we are preparing for the beam test.
Yeah, exactly. Yeah.
And how do we check if it is centered? Is it central?
We press the burst button.
What do you mean burst button? It is starting point.
Yeah.
Okay.
But we press the burst button.
Burst.
Yeah.
Oh, okay.
Yeah, and look at the spot. Yeah. If the laser spot is in the center, everything is fine. Yeah. If it's off center, we need to adjust the beam. We repeat the process until the spot is exactly in the center.
Ah, I see. This step ensures the laser and the gas are perfectly aligned. Okay.
Yeah, yeah. And this directly affects cutting quality. And all right, that is all the preparations before cutting.
Okay, got it.
Yeah. And now we can move into the cutting process. Yeah. And the first step, we talk about import drawing.
Importing, okay.
Yeah, import drawing. It's okay for all the software. Is the same process.
Yeah. Yes,
we click file, then import the drawing file. The system supports formats like the XF, DWG, PLT, and NEC, and this. Then we select the part drawing and choose the unit, either metric or inch.
So this is where the job starts.
Yeah, exactly. Yeah.
And after importing the drawings, what's next?
Next, we need to setting the graph.
The graph.
Yeah.
Okay.
Yeah. We select all graphics and assign them to a layer. Usually, we set them to the same layer first. For very small feature like small holes, we can also use different layers. Yeah.
And let me say, this just help us manage different cutting strategies, right?
Yeah. Yes.
Okay.
And next step, lead.
Yeah, lead.
We select the graphics, then click lead. We set the lead in type, line, or arc. Yeah, and then define the length and the angle, and after that, obviously click OK.
Okay.
Yeah.
So this controls how the cut starts.
It helps protect to the edge quality.
Okay.
Yeah.
What about the gap and the micro joint between parts?
Yeah, gap.
The metal parts.
Gap is the starting point of a cutting. Micro joint is used to connect parts during cutting. This prevents small parts from moving or tripping. We select the graphics, set the gap or micro joint, and confirm.
And this is mainly about the stability of the metal parts during cutting.
Yeah, yes, exactly.
Okay.
And now we talk about compensation. We need to click compensation, then set the compensation type, and define inner and outer width. This adjusts for the curve. The material removed during cutting.
And this part is, let me see, it ensures the dimensional accuracy.
Accuracy.
Okay.
Yeah. Yes. Next step, birth. We need to click birth and then choose the starting position, like lower, right, center, or others. This defines where the cutting starts relative to the sheet.
Okay, got it. And it helps align the job with the material.
Yeah, yes. And then sorting. We right click and select sorting. Yeah. Then choose the cutting order strategy. And after that, confirm.
Okay. For this part, it may seem very simple, but it's very important, right?
Yeah.
This decides which parts is cut first.
Yes, a good cutting order improves efficiency and reduces deformations. Now, Dennis, we move to parameter setting. We open the layer setting panel, then import the parameter library. And choose parameters based on material, thickness, gas, and nozzle. And after that, confirm. Yeah.
I think the parameter setting part is very difficult
but
for some beginners, right?
Yeah, it's important to explain it. Yeah. So we start talk about calibration.
Okay, calibration.
Calibration. First, confirm the nozzle is correct first. And then move the cutting head about 10 millimeters above the sheet. And click calibrate.
About 10 millimeters above the sheet.
Yeah.
Okay.
After that, check the result, especially stability and smoothness.
Okay.
And this need to be good, very good.
Okay, I see. And by this way, we can ensure the heat control is working properly, right?
Yes, yes. And all right, now let's move to edge finding.
Edge finding.
Yeah, another important parameter.
Seems very advanced technology. Right?
Yeah, yeah. And because the sheet is not always perfectly aligned, so we need to detect the real position before cutting. First, we move the cutting head to the corner of the sheet, and then click Edge Seek, Edge Finding,
Edge finding. Okay.
Yeah. Enable Edge Finding and select Auto Mode with the 3-point type. Then set parameters like sheet size and finding speed. And after that, click Start.
And what do we get after that?
We get the actual position and the rotation angle of the sheet. And then we can click OK and start.
Okay. So now the system knows exactly how the sheet is placed in the above the table, right?
Yeah, exactly. Yeah.
All right, what's next?
Next, we talk about frame. We click Frame. The machine will move around the cutting area. During this process, we need to check the red light. The red light stays on the plate.
So the frame, you mean the frame of the sheet, right?
Yeah.
The metal sheet. Okay.
Yeah.
This is to make sure the cutting parts is placed correct.
Going out. Yeah.
Okay.
Yes.
Okay.
And also to avoid going outside the sheet.
Yeah. Okay.
Yeah. And next step, we talk about simulation. Yeah. We click simulation, then we observe the cutting path inside the software. We check if there is any abnormal order or unexpected movement.
Okay.
Yeah.
So this is like just a dry run.
Yes, yes, exactly.
Okay.
No risk, but it's very important.
Yeah, yeah.
Yeah.
And now are we ready to start cutting?
Yeah, but first we need to test cutting.
One more test. Okay.
Yeah.
Okay.
Before starting, we use the gas blowing about 3 times to clean the nozzle. Then we frame again to double check the position. After that, we click Start and we carefully observe the first cut.
Seems we have to prepare very carefully before we just start cutting, right?
Yeah.
And we don't go straight into full production.
Yeah, exactly. We always verify the first part. We check it. We check if the cutting quality and dimensions are correct. Yeah, and that's all the procedure, and that is all the procedure in this part.
Okay,
yeah.
I see.
Now we can cut. We can start cut. Once cutting is completed, we remove the finished parts from the sheet, and we need to make sure the parts are fully separated, and handle them safely. And after unloading, we can move on to the shoot-down. Yeah. First, we stop the cutting program from the software. Make sure all operations are finished before moving to the next step. And then we turn off the laser source. This is the core part of the machine. It's important. So if it needs to be shut down properly. Yeah. Next, we turn off the chiller. This stops the cooling system after the laser is powered down. Yeah. Then we close the cutting gas. Make sure all gas valves are fully shut. Next, we can turn off the electrical cabinet. This cuts off the machine control system. Yeah.
That's all?
Yeah. If you are using an air compressor, turn it off as well.
Okay.
Yeah. If there is a voltage stabilizer, turn it off next.
Okay.
Yeah.
Okay.
Finally.
Finally.
Yeah.
Okay.
Finally, turn off the main power switch. This completes the shutdown process. That's all.
Okay.
But before we wrap up, there is one more important point we want to highlight. That is, even during normal cutting, monitoring is something you should never ignore. That is what we call resume. Continuous monitoring during operation. Continuous. Because even if everything is set correctly, conditions can still change during cutting.
Yeah, of course. Okay.
Yeah, we need to see. So this is not just something you do once. It's something you keep doing during the entire process. Yeah, and this is what helps you catch problem early. Yeah, before they affect cutting quality or damage the machine and for your safety. Yeah. So we can start. We can check the laser head status now through the software or mobile app. We monitor key values like focusing length, collimating length, laser output, cutting head temperature. All values should stay within normal range. Yeah.
And with all these values to monitor, what if something goes wrong?
If there is an alarm, we should stop cutting immediately and contact the service engineer. Yeah.
So monitoring is continuous and not just at the beginning, right?
Yeah, exactly.
Okay. All right. So that's the full cutting process, right? From the importing the drawing of the graph to setting parameters, calibration, edge funding, and the final cutting and monitoring. Every step plays a role, right?
Yeah. Yes. If each step is done correctly, you get stable cutting and consistent result. Yeah.
Now we have just completed the full operation process, and how about let's move on to the next part?
Yeah.
Okay. All right, guys. So we have just finished the machine operation part. Now here's something I really want to ask you. Have you ever done everything correctly, but still ended up with a bad cutting results? I think it's very common, right? Yes, this happens more often than you think. In many cases, the problem is not the machine. It's not even your parameters. It's the gas. So Frank, how big a role does gas actually play?
Yeah, it plays a huge role. In fact, I will say it's one of the key factors that defines your final result. You can have a perfect setup, perfect parameters, everything looks right. But if you choose the wrong gas, the cutting result will still be wrong. Yeah, because acid gas is not just there to blow molten material away. It's actually a change how the cutting process works. Is the cutting process.
Ah, that's
Yeah.
interesting. So
Yeah.
it's not just a supporting role; it's the part. It's a part of the process
cutting.
itself.
Yeah.
Okay. Okay.
Yeah.
So questions for everyone watching. What gas are you using most right now? Oxygen, nitrogen, or air? Type it in the chat.
Yeah. Talk about the laser. In the laser cutting, we mainly use three gases: oxygen, nitrogen, and air.
Air.
These are three gases.
That sounds simple, but I guess they behave very differently.
Yeah, yes. Each gas creates a completely different cutting mechanism. And to make it easy to understand, I usually explain it like this. Oxygen helps you cut thicker. Nitrogen helps you get better quality. And air helps you reduce cost. But,
Okay, seems it's very easy to remember. Let's go step by step, okay?
yeah.
And let's start with the carbon steel, since I think that's what most people are cutting.
Yeah, sure. When it comes to carbon steel, you actually have three options. Yeah, but each one gives you a completely different result. Yeah. We can start with the talk about oxygen. Oxygen is usually the first choice when you are cutting thick carbon steel. The reason is that oxygen reacts with the metal. This reaction generates extra heat. Yeah.
Extra heat.
Extra
okay.
heat.
Okay.
So now it is not only the laser doing the cutting. The gas is also adding energy into the process. It's a part of the cutting.
Yeah.
Yeah.
So that's why oxygen can cut thicker material?
Yes. That extra heat makes a big difference. And another advantage is that the cutting surface can be smoother and even a bit shiny.
Okay.
Yeah, but the trade-off is that the cutting speed is usually slower and the parameters are a bit more sensitive.
Okay,
Yeah.
got it. So oxygen is really about thickness. And what about nitrogen?
Nitrogen is a completely different approach. It does not react with the material at all. So there is no oxidation happening. That means your cutting surface stay clean and there is no discoloration of slag and the metal keeps its original color. Yeah.
So this is more about quality, the cutting quality, particularly for thin or medium thick carbon steel plates.
Yeah, it's expensive. If your customer cares about appearance, nitrogen is usually the better choice. But of course, nitrogen comes with the higher cost.
Okay.
Yeah.
So makes sense. And then we have air, the third gas we almost use.
Yeah, air is the most cost-effective option. Yeah, it's easy to use and relatively fast. But since air contains oxygen, the reaction is no controlled. So you often get darker edge, rougher surfaces, and sometimes slag on the bottom.
Okay.
Yeah.
So for carbon steel, it really depends on the customer's need, right?
Yes. If you want to cut thicker plates, go with oxygen. If you want better surface quality, nitrogen is recommended, especially when cutting thin carbon steel. If you want to reduce cost, then air is a practical option. Yeah.
So let me ask everyone who is watching, in your daily production, what do you care more about, quality or cost? Type it in the chat. I'd love to see you answering. So, all right, let's move on to the stainless steel. Is the logic just the same?
Not exactly.
Okay.
For stainless steel, the choice is actually much more straightforward. In most cases, nitrogen is the standard option because stainless steel is very sensitive to oxidation. If you use nitrogen, you protect the surface from reacting with oxygen. So the result is a clean, bright, high quality edge. Yeah.
And if someone uses air instead?
You can use air, but the surface will become darker. So the overall appearance is not as good.
And what about oxygen?
Oxygen is generally not recommended for stainless steel because it will cause oxidation, and that directly affects the surface quality.
Yeah, it makes sense. So if appearance matters, nitrogen is really the only choice, right?
Yeah, exactly. Yeah, exactly. And all right, let's talk about aluminum. For aluminum, nitrogen and air can be used. In terms of cutting speed, they are actually quite similar. The difference is mainly in the result and the cost. Nitrogen will give you a cleaner and more stable cutting surface. Air is cheaper, but the surface quality is not as good.
Yeah, so again, it's a trade-off, right?
Yeah, always. Yeah.
And what about the brass?
Brass. For brass, nitrogen is usually the better option because it prevents oxidation and helps keep the original metal color. Air can still be used, but the surface will darken. And there is one very important thing to remember. You should not use oxygen for materials like aluminum or brass.
So why is that?
Because oxygen can create unstable reactions with these materials. In some cases, it can even be dangerous. So this is not just about cutting quality, but also about our safety. Yeah.
Okay, safety matters most, right?
Yeah.
It's really important.
Yeah, the first.
So if we simply simplify everything we talk about today, we can conclude that how should someone make a final decision?
It comes down to three things: cost, quality, and efficiency. You always need to find a balance between them. You cannot maximize all three at the same times.
Okay. That's very clear way to think about it.
Yes. Let me give you a few simple examples. If you are cutting thick carbon steel, oxygen is usually the best choice.
Yeah.
If you are cutting stainless steel and care about surface quality, go with nitrogen.
Yes.
If you are doing large volume production and want to reduce cost, air is the good. In this case, is a good option. Yeah.
Yeah. Just very practical and easy to understand.
Yeah.
Okay. So what I was showing you here is not just which gas to use, but how to think about gas selection, because this decision directly affects your cutting quality, your efficiency, and your cost. So, and now here's the next question. Even if you choose the right gas, why do some costs still fail? And why does the thick plate cutting still struggling in real production? That's where parameters come in. And in the next part, we are going to focus on how to set the right parameters for our topic today, the 30 kilowatts machines.
Yeah.
Especially when cutting thick materials, we will show you what really makes the difference between it cuts and it cuts well.
Yeah.
All right. We have covered the gas selection, and let's move into the next critical part, parameters. Because in real production, choosing the right gas is only the first step, and what really determines the final result is how you set your parameters.
Yeah.
And before we get started, I want to clarify one important point. There is no universal parameter setting.
Yes, exactly.
Yeah.
Every thickness requires its own setup. So what we are going to do here is very practical. We will go case by case, different thicknesses, different parameters, and then show you the actual cutting results.
All right, and let's move into the carbon steel with oxygen. This is where thick plate cutting really happens.
Yeah.
And also, before we go into different thickness, there is one thing we need to understand first. Focus, the laser focus.
Yeah.
Frank, a lot of people here maybe may hear positive focus, negative focus, but they are not really sure about what it means in practice.
I can explain it in a very simple way. When we say positive focus, we mean the laser focus is slightly above the cutting area.
Okay.
Yeah, when we say negative focus, the focus is placed deeper inside the material.
Okay, understand.
Yeah, and this change how the cut behaves. With positive focus, the opening at the top of the cut becomes slightly wider. That makes it easier for oxygen to flow into the cut. And that is important because oxygen cutting depends on a stable reaction. With the negative focus, the energy is pushed deeper into the material. So the laser cuts more strongly inside the plate.
Okay.
Yeah. In simple terms,
Yeah.
positive focus helps the reaction stay stable. Negative focus helps the cut go deeper and faster.
Very
Yeah.
clear. Okay. So one is about stability.
Yeah.
And the other is about cutting strength.
Yeah, cutting strength, exactly.
All right. Now let's see how does this work with real thickness. Let's start with our thickest material, 60 millimeters
yeah.
carbon steel.
Yeah. At 60 millimeters, we usually start with positive focus. Yeah.
Yeah.
Because at this thickness, the biggest challenge is not speed, it's stability.
Yeah, stability.
Yeah. So the setup looks like this. The focus is set to 26 millimeters. The cutting speed range from 0.2 to 0.6 meters per minute. And we are using a single layer 2.5 nozzle. Yeah. Lower speed helps the oxygen reaction stay consistent, and the smaller nozzle helps control the gas flow.
Okay.
Yeah. If the process becomes stable, you can try negative focus. In that case, the focus is set to minus 25 millimeters. The cutting speed range from 0.5 to 0.8 meters per minute. And we are using a single layer 3.5 nozzle. This increases cutting strength, but it also makes the process easier to lose control.
So for 60 millimeters, you don't start with the speed, you start with stability.
Yeah, exactly.
And let's look at the real cutting results with the cutting demo video.
This is where 30 kilowatts shows its capability, but only when the parameters are correctly matched. Yeah.
Now let's move to the air cutting. Okay, starting with the 20 millimeters.
Yeah. Air is a more cost-effective solution, but the cutting behavior is different again. Because air contains oxygen, but not in the same controlled way as a pure oxygen cutting. So you get some oxidation, but not the same reaction quality as a oxygen. For 20 millimeters, the setup is the focus is set to minus 7 millimeters. The cutting speed ranges from 4.5 to 6.5 meters per minute. And we are using a single layer 5 nozzle. At this thickness, air cutting is usually much easier to run. And since penetration is no longer the main challenge. the focus shifts more toward speed and production efficiency.
I think the parameters, the numbers are quite hard to remember, right?
Yeah.
So for the audiences in the live streaming, if you like to get the parameter settings, you can tell us in the comment section. Our experts will give you answers, or leave your email address. We can send you an email with the parameter settings. Okay, so let's take a look at the cutting results. And now we have looked at the carbon steel with oxygen and air. I think the difference is much clearer now. Right?
Yeah, exactly. For the same material, once the gas changes, the cutting logic changes. And once the thickness changes, the parameter setup changes as well.
So there is no single answer for carbon steel. And you always need to look at the three things together: the material, the gas, and the thickness. Right?
Yeah, that is exactly right. And
all right, now that we have covered carbon steel, let's move on to another material, stainless steel, right?
Yeah.
Okay. We will start with the 20 millimeters using nitrogen.
At 20 millimeter, the cutting process is already quite stable. Yeah, the setup is the focus is set to minus 10 millimeters. The cutting speed ranges from 3 to 7 meters per minute. And we are using a single 5 nozzle. For stainless steel, the main goal is to avoid oxidation. Yeah, that's why we use nitrogen. At this thickness, you can already run at a relatively high speed while keeping a clean cutting edge.
Now let's take a look at the actual cutting results with the video. Okay.
Yeah.
You can see the surface stays bright and clean.
Yes, that's exactly what nitrogen cutting is designed for.
Yeah. Now let's take a look at the 40 millimeters using nitrogen, but using air instead of nitrogen.
Yes, for 14 millimeter stainless steel with air, the setup is the focus is set to minus 17.3 millimeters. The cutting speed ranges from 0.8 to 1.8 meters per minute. And we are using a single layer 5 nozzle. Air cutting is more cost effective, but the cutting behavior changes because air contains oxygen. Yeah, for this reason you will get some oxidation during the process. So the surface becomes darker and the edge is not as clean as a nitrogen.
And this is another very clear trade-off. Okay.
Yeah.
Lower cost, but lower surface quality.
Yeah. Exactly.
So what about, let's take a look at the results, also with the cutting video. So for stainless steel, the logic is quite clear. If you want the best surface quality, nitrogen is the standard choice. And if you want to reduce cost, you can use air, but you need to accept some oxidation.
Yeah, and just like we saw with the carbon steel, parameters always need to match the thickness.
All right, so now we have covered both carbon steel and stainless steel, and you have seen how parameters change with thickness and gas. But here's a question about a lot of customers ask, if we already have the right parameters, what difference does a high power actually make? Is 30 kilowatts just about cutting thicker material, or can it also improve speed? And more importantly, how big is the difference in real production? Okay, now in the lecture part, we are going to show you a direct comparison. The 20 kilowatts versus 30 kilowatts. Yeah, cutting the same material under real factory conditions. And you will see exactly where the extra power makes a difference. Okay, now stay with us.
Yeah.
This is where it gets really interesting. All right, let's get to the questions we hear about all the time. If we already have the right parameters, what does high power really gives us? Is the 30 kilowatts just about cutting thicker material, or can it actually make a big difference in speed? So instead of just talking about it, let's show you. We are going to compare 20 kilowatts and 30 kilowatts under real factory conditions, same material, same thickness, and same cutting logic. And you can judge the difference by yourself. Let's start with the carbon steel, 20 millimeters using air. So first, we will look at the 20 kilowatts.
Yeah.
Okay.
Yeah. Yeah, 20 kilowatts. The cutting speed is around 2 to 3 meters per minute.
Now let's switch to 30 kilowatts.
With 30 kilowatts, the speed increased to around 4.5 to 6.5 meters per minute.
That's almost more than double in some cases,
yes,
right?
And this is not just about speed on paper. This is directly translated into higher productivity.
So for the same 20 millimeters carbon steel, and the 30 kilowatts can significantly reduce processing time. Now let's move to the another material, stainless steel with nitrogen. So also first 20 kilowatts.
20 kilowatts stainless steel.
Yeah.
Stainless steel, we are looking around 3 to 3.2 meters per minute.
Now let's see 30 kilowatts.
For 30 kilowatts, the speed increases to about 4 to 5 meters per minute.
So again, we can see a clear improvement.
Yes,
Right?
and especially for stainless steel, higher power helps maintain speed and cutting quality.
And what does this really mean in practice?
High power is not just about cutting thicker plates.
Yeah.
It's about cutting faster, reducing cycle time, and increasing output. If you are running production every day, this difference adds up very quickly.
Yeah.
Yeah.
Exactly over time, right?
Yeah.
This can make a big impact on overall efficiency and cost.
Yeah.
So if you are just currently using a 20 kilowatts, the question is not just can you cut. The real question is how much time could you save with higher power, and how much more could you produce? That's something worth thinking about. So let's move on to the next part. Okay, now we have gone through the machine operation, gas selection, and parameter optimization, and I think this is the right moment to step back and ask a broader question. why in thicker metal applications does laser so often become the stronger road compared with plasma? And rather than answering that in a vague or overall general way, we'll break it down into our 4 very practical points. We'll look at curve width, cutting speed, small round holes, and finally the sharp corners on gear-shaped parts. So Frank, before we get started, let's have a break, right?
Yeah.
Can we have a break?
We can have a break. Yeah.
We have just to go through a lot of knowledge, right?
Yeah.
It's maybe hard to remember. And one more one more mention for our audience.
Mm-hmm.
If you like to get the how to set the parameters, or you are interested with our knowledge, you can send comments in the comment section and leave your email address. Also, you can send us an email to info@bodor.com. We will send you knowledge with the documents. Okay.
Yeah.
So let's have a rest. So Frank, now time to get back to life.
Yeah.
Okay, let's start it with the curve width, and this is where the difference becomes very clear.
Yes, for thick carbon steel, about 20 millimeters, plasma cutting typically has a curve of around 5 to 6 millimeters with a 30 kilowatts laser. It's about, with the laser, with 30 kilowatts laser, it's about 1.5 millimeters.
So plasma is about 4 to 5 times wider.
Yeah, and then difference means direct material loss.
So narrow curve means lower cost.
Yes.
And next, the cutting speed. We have summarized the data here.
Across different thicknesses, laser cutting is consistently faster than plasma. And this advantage becomes even more obvious as the thickness increases.
So it's not just faster in theory. In real production, it directly improves the production efficiency.
Yes.
Now let's look at the small holes.
With the laser cutting, the minimum hole diameter can be as small as 50% of the plate's thickness. But with plasma, small holes are very difficult. Usually they require secondary processing like drilling or grinding. Yeah. So the laser can complete the part in one step, no secondary process.
Yes.
Yeah.
And let's look at the real example.
Okay.
Can we? And this is the 500 millimeter diameter plate, the circle plate with in 25 millimeter thick carbon steel, with 50 small holes ranging from 4 to 10 millimeter. All processed directly by laser, no secondary operation needed. And let's give you another sample. Sharp corners.
Sharp corners. Laser cutting can produce sharp edges without overburn, but plasma cannot achieve sharp corners.
So for parts like gears, this makes a big difference. Let's look at this example.
Yeah.
And this is a 500 millimeter gear, 12 millimeter thick carbon steel with 42 sharp teeth and a corner radius of just 1 millimeter.
Yeah, laser can achieve this directly with the clean and precise edges.
So to summarize, compared with plasma, laser gives you narrow curve, higher speed, and better precision for small features.
Yeah.
And also the ability to handle complex shape.
Yeah. And beyond these, laser also offer better cut quality, less deformation, less post-processing in a one time, and a cleaner working environment.
Yeah. So it's just not just about cutting; it's about improving the entire production process.
Yeah.
Now let's move on to our real customer case, so that we can place the technical discussion into an actual industrial setting. We will look at the example of the Altec GmbH in Germany. This case is useful because it shows that adopting a 30 kilowatts platform is not only an equipment upgrade, it also a change into production organization, more autonomy and more internal control and less dependence on outside processing. Then let's watch this video of our customer interview.
Okay.
Wir haben den Laser von der Firma Bodor, ist ein Jahr bei uns im Einsatz. Wir konnten bisher jede Störung durch den Service relativ schnell selber lösen und ich kann den Laser der Firma Bodor weiterempfehlen. Ich bin Daniel Schnebel, bin Geschäftsführer von der Firma Altec. Wir sind ein familiengeführtes Unternehmen. Wir stellen Verladeschienen und Überfahrbrücken aus Aluminium und Stahl her. Wir fertigen bei uns von Losgröße 1 bis zu Großserien alles selbst bei uns im Haus. Wir haben eine sehr hohe Fertigungstiefe und haben seit einem Jahr einen Bodor Laser P30 kW bei uns im Einsatz. Wir waren auf der Suche nach einer Laserschneidanlage und ich hatte dazu Kontakt mit der Firma Bodor, habe dann mit Referenzkunden gesprochen. Die Referenzkunden konnten mir bestätigen, dass die Bedienung der Maschine sehr einfach war, dass die keine Fehler aufgetreten sind bei der Maschine und dass die Maschine sich wirtschaftlich sehr gut rechnen lässt. Die Veränderungen bei uns im Unternehmen sind dadurch, dass wir die Fertigungstiefe erhöhen konnten. Wir konnten Teile, die wir extern gegeben haben, in-house fertigen. Die Produktionszeiten konnten dadurch verkürzt werden und wir konnten gestalterisch Bauteile überarbeiten und ins 21. Jahrhundert bringen.
So here again, 30 kilowatts is not just a performance concept. It is also a production structural concept.
Yeah, exactly. That is why cases like this matter. Yeah.
All right, I think the core of today's webinar is very clear now. We have started from a very from a very clear thing, how to cut thick metal with 30 kilowatts.
Yeah.
And
parameter
we have
optimization. Yeah.
Yes, and we have also developed the two real centers.
Yeah.
First, how to properly use a 30 kilowatts laser cutting machine with operation step by step, and second, how to set and optimize cutting parameters for
carbon steel, stainless steel.
Yeah.
And
and just as importantly, we made the cutting scope split throughout the two sessions.
Yeah.
The first is 20 to
60 millimeter carbon steel and
then 20 to 40 millimeter
stainless steel.
Yes.
Stainless steel.
Now before we close, let's move into a short question and answer segment, and also respond to your comments, typical questions from our viewers watching the live session. Question 1: If I mainly process medium thick material today, and when does it really make sense to move to or upgrade to a 30 kilowatt machine?
This question is a very practical question. A 30 kilowatt machine becomes especially meaningful when your work is moving more often into a thick plate when you need a stronger cutting efficiency or when you want better production capacity across a wider thickness range. So this decision is usually not only about maximum thickness. It's also about whether your production now requires more speed, more stable cutting of thick material, and more room for future jobs that lower power machine may handle less efficiently. Okay.
And here is another question. This time from an existing laser user who has already have the laser cutting machine. The question is, I already have a laser cutting machine. If I am thinking about upgrade to a high power laser, what should I evaluate first?
I would look at three things.
Yeah, three.
First,
three things. Okay.
Yeah. First, your actual material mix, your typical thickness range, and your production bottlenecks. If your current machine is already limiting you on thick carbon steel, thick stainless steel, cutting speed, or final part consistency, then an upgrade starts to make sense. In other words, the question is not simply whether a higher powered machine is available. The question is whether your current equipment is holding back the work you actually need to do.
Yeah.
Yeah.
And let's turn to the third question, which is also very common. Can one 30 kilowatts machine handle both carbon steel and stainless steel well, or does the performance depend too much on the material?
A 30 kilowatts machine can absolutely handle both well, but the process logic has to change with the material. What is exactly why today we separated machine operation, gas selection, and parameters optimization. For carbon steel, especially at greater thickness, oxygen often becomes a key part of the process. And about stainless steel, nitrogen becomes important for section quality and the finish. So yes, one machine can cover both, but only if the process is adjusted correctly for each case. Yeah.
And here we have got another question from the live audience. Is the value, is the advantage of the 30 kilowatts only about faster cutting?
No. Faster cutting is a part of the value, but it is not the full value. The real value is broader than speed alone. It includes better thick plate capability, more stable penetration, cleaner geometry, less rework in many cases, and a stronger overall production flow. So if someone looks at 30 kilowatts only as a speed upgrade, that is too narrow. It's the real important. The real important is that it changes what you can do, how consistently you can do it, and how efficiently the whole process can run.
Okay, and let's take one more question for customers who are just beginning to work with thick metal. What is the most important point to get right first?
I will say this very clearly. Do not begin by thinking only about power.
Okay.
But begin with the correct machine operation, correct gas selection, and correct parameter logic. Because even with high power, thick metal, cutting does not become truly useful unless the process is controlled properly. Once the workflow is correct and the parameters are matched to the material, then the value of 30 kilowatts really starts to show.
So if we put all today's discussion into one simple conclusion, it will be this: 30 kilowatts for thick metal cutting is not only about a high power, it's about using the power in the right way, with right process logic behind it.
Exactly. That is where stable cutting, better part quality, and stronger production efficiency really come from.
Okay, thank you. Thank you again to everyone who joined us for today's live session, and also thank you very much, Frank,
Thank you,
as well for your question. And once again, don't forget to our special self-service live stream later this month. Don't forget to send the code GLOBAL1 to info@bodor.com to claim your exclusive webinar offer and get the event details in advance. And make sure to follow Bodor Laser on Facebook, YouTube, LinkedIn, and TikTok for more live demos, tutorials, and updates. Alright, everyone, this is just for today's Bodor Laser Academy Live. Thank you all for being with us today. I'm Dennis, and thank you again, Frank.
I'm Frank Vitale. Thank you, Dennis.
Thank you. Okay, and we will see you at the next webinar. Bye-bye.